Okay, so the next one is corollary 4. Let us recall that in the previous vector space video, we have already seen that if we are in a finite dimensional vector space, then any two bases have the same number of elements, and that number has been defined by us to be the dimension of the space. Now in this one, we are given two finite dimensional vector spaces over a common field F, and they have the same dimension. Then this corollary asserts that they are isomorphic, they have to be isomorphic. This is quite unlike what we have, for example, in group theory. In group theory, two groups having the same order does not guarantee that they have to be isomorphic. One simple example of that fact is your these two groups Z6 and S3. This is your cyclic group of order 6, and this is your symmetry group of degree 3, which also has order 6. This is abelian, this is non-abelian, so they cannot possibly be isomorphic. Here, however, same dimension implies isomorphic. So let us see the proof. The dimension is not given, okay, we will assume it to be n. Let both the spaces have dimension n. Okay, now we have already seen that if a vector space has dimension n over a field F, then it is isomorphic to the space of n tuples over F, Fn. So these two vector spaces will also, each one of them will be isomorphic to Fn. Then both the spaces are isomorphic to Fn. Hence, they are isomorphic to each other. And this is just the proof. Now if we want to absolutely see what is going on behind this line, although it is something very easy, but still, then this is what is going on. Say your spaces are V1 and V2. Then there is an isomorphism between V1 and Fn, and there is an isomorphism between V2 and Fn, F and G, say. Then because G is an isomorphism, its inverse exists and is an isomorphism between Fn and V2. So we can now take the composition of F and G inverse. That will give us an isomorphism between V1 and V2. Now here I want to say something which we have in fact seen many times, but still the whole mathematical world, almost the whole mathematical world is familiar with this way of writing the image of an input x under a function f. F of x, we in fact say it also like that. However, in this text we are writing the input to the left of the function. So that is why our composition looks like this. The composition follows the natural order in which the functions are acting on the sets. For example, f takes us from v1 to fn, and then G inverse takes us from fn to v2, so that f composition G inverse ultimately takes us from v1 to v2. That intermediate thing is there, of course, we understand, that is why, that's how this composition has been defined. But because our input comes first, so it makes sense to write f first and then G inverse, because you are applying f first to x and then to that you are applying G inverse. However, for us who are using the more familiar notation, you have to change this order, because if you are using this notation, then in this way only you can apply f first and then on that you can apply G inverse. Anyway, so we have seen the proof, and now next the author asks this question: how much freedom do we have in choosing a basis of a finite dimensional vector space? That is, if we are in a finite dimensional vector space, we know that there is a finite basis, and in fact there are multiple ones, but all of them have the same number of elements. These are things we already know, but how can we find out a basis? And one result, this next one, says that, say this is your vector space V, in which you manage to find some linearly independent vectors. There may be only one vector or several million vectors, it does not matter, but some linearly independent vectors. You have found a linearly independent set in V. Then this next result says that either they themselves form a basis of V, or you can bring in some extra vectors from outside. Outside means from outside of this set, finitely many of course, so that this larger set is a basis of V. In other words, if in your vector space V you find finitely many linearly independent vectors, then you can blow that set up to a basis of V. That is this next lemma. Four, 2, 5. If V is finite dimensional over F, and some m vectors u1, u2 up to um in V are linearly independent, then you can find some extra vectors. Then we can find vectors um plus 1, um plus 2 up to say um plus r in V, such that the corresponding larger set is a basis of V. Let's now see how we can prove this, or of course how the author has proved it. So we start off with the fact that V is finite dimensional, so it will have a finite basis since V is finite dimensional. It has a finite basis. If you find this a little disturbing, I mean to call this list a basis, you can of course use the curly brackets and make it properly a set. The set is a basis. In fact, truly speaking, that's what a basis is. It's a set, not just a list. But we are also being a little lax in our notations like Herstein. You understand what we are trying to say. So we write like this without using brackets. So this is a finite basis. Now, being a basis, it has two properties. Now, these vectors span V and they are linearly independent. We are going to now use the span part. Since these VI's span V, so a larger set also spans V. Also spans V, which is obvious because the VI's are already spanning V, so some extra vectors will not actually affect anything, and that is because those extra vectors are actually coming from inside V, not from outside. So the span is not affected. Hence, so we are now going to recall a previous result which we have already used one or two times by corollary 1 to theorem, what was the number, 421. V has a basis of this form. IR. So now it's clear to prove the lemma. So the extra vectors that we were talking about in this statement are just these extra vectors. We merely take m plus 2 as vi2, etc. Okay, so that means our linearly independent set consisting of these m number of u's has been blown up to this basis. Keep in mind that these extra vectors you may not need. It may happen that these u's themselves form a basis. That is, besides being linearly independent, they in fact themselves manage to span the whole space V. That may also happen. So these extra vectors may not be there, but if the need arises, we will always find finitely many extra vectors so that their introduction will give you a basis. Now, one more thing is there. How exactly we have used this corollary 1 to theorem 4 to 1? Let's just see that also. And since the statement of this corollary is a little involved, so we may not remember it. So let's see that. Let's briefly recall what this corollary says and how exactly we are using it here. The statement of the corollary is, it was this. There were some vectors v1, v2, etc., vn. Do not confuse these v's with these v's. Okay, these are some vectors. They are not necessarily any basis or anything here in this statement. They are just simply some vectors. We are not even saying anything about their linear dependence or independence or their span. Simply a collection of vectors in a vector space V. And one more thing here is that this V in our corollary is not necessarily finite dimensional or anything. That is not mentioned. It is just any vector space. And it is given that W is the linear span of these vectors. Okay, so these are some vectors in a vector space V whose linear span is W. W, however, is bound to be finite dimensional because it is being spanned by finitely many vectors, and in fact that is the definition of finite dimensionality. Additionally, what is given is that the first k vectors in this list are linearly independent. That is given. Then the corollary states, it asserts that there is a subset of this set or this set of n vectors which looks like this. Vk let us for once write it properly as a set. A subset of these vectors exists whose elements are linearly independent and whose linear span is equal to W. In other words, there is a basis of W of this form. That's what this corollary says. Now, exactly how we are using this here is of course somewhat understandable, but let's just see precisely what we have done here. In our case, these vectors are these vectors. Okay, and the W that we have, which is their linear span, is actually just V, right? And this part, that the first k are linearly independent, is here. These vectors are, the first m are linearly independent. So what the corollary says is that W will have a basis of this form. So that means our V will have a basis of what form? The first k linearly independent vectors must be in that basis. So the ui's are in the basis, and additionally possibly some other vectors. So from these vi's we have taken some possible vectors if they exist. So that's how we are getting this basis, and that's exactly how we have concluded this thing from corollary 1 to this theorem. Okay, so that is the thing. Now next comes the issue of this. Say you have a finite dimensional vector space, you can apply a homomorphism, not an isomorphism, but in general a homomorphism, to map this vector space into, say, another vector space, in which you will have an image of this homomorphism. Or to make matters simple, you can have an onto homomorphism, a surjective homomorphism, so that V prime is a homomorphic image of V. Now we have already seen in some previous theorems that these homomorphic images have a special structure. They all look like this, where W is a subspace of V. In fact, this particular homomorphism, this onto homomorphism, it will have a kernel. No? That kernel, say that kernel is K. That K we already know is a subspace of V, and such that the quotient space V by K is actually isomorphic to V prime. And that is why we say that all the homomorphic images are actually this. So that is why when we talk about a homomorphic image of a vector space, we take the quotient of the space by a subspace. The same thing you have already seen also in groups, where a homomorphic image of a group is the group quotiented by a normal subgroup, or in case of rings, where the homomorphic image is the ring quotiented by an ideal. Okay, so now the question here is, if we have started with a finite dimensional vector space V, then what about the dimension of this homomorphic image? But before that comes the question, is the homomorphic image also finite dimensional? It is, and then we will also say what its dimension is precisely, and in the course of that we will also say that something about the dimension of W itself. So those are the next things. The word dimension is, of course, in a sense, it somehow measures the size of the space. and this same word has different meanings. Here in vector space, dimension means something. In topological spaces also we have a notion of dimension, Hausdorff dimension. In rings also we have a notion of dimension. And there are fractional dimensions also in fractal structures. Hopefully at some point we will reach those things to at least see what they are. But right now let's just see this next result. So this is lemma 6. If V is finite dimensional and W is a subspace of V, then W is okay. If V is finite dimensional and W is a subspace of V, then W is finite dimensional dimension of W is less than or equal to dimension of V, which is natural. No, W is a part of V and we are saying that V is finite dimensional, that is the dimension that is measuring in some sense the size of V is finite. So W should also be finite dimensional, and in fact its dimension should not exceed the dimension of V. And in fact the homomorphic image, this is also finite dimensional and its dimension is equal to the dimension of V minus the dimension of W. And this formula reminds us of logarithms. Okay, so let us just see the proof. So again we start with the finite dimensionality of V. Let n be the dimension of V. Then by what is that result? By lemma 4 to 4. Any n plus 1 elements or vectors in V are linearly dependent because the dimension is the maximum number of linearly independent vectors in a vector space. If you go beyond that number, any such set containing a larger number of vectors, then the dimension must be linearly dependent. In particular, any n plus 1 elements or vectors in W, if we happen to choose those n plus 1 elements in the subspace W, they are also going to be linearly dependent in W are linearly dependent. So the maximum number M, say, of linearly independent elements in W is finite. Of course, because the moment you take n plus 1 elements in W, those elements give you a linearly dependent set. So you cannot choose that many elements and have a linearly independent set. So there is a maximum size of linearly independent sets in W. Let that maximum size be M. If we go beyond M in W, then you get a linearly dependent set, and that M of course is finite, and in fact M is less than or equal to N. And because we are saying that M is the maximum number of linearly independent elements in W, so we should be able to actually have some such number of elements, that many elements. Let W1, W2 up to Wm be linearly independent. Okay. Now what we aim to show is that these, of course, by our very choice, these vectors form a linearly independent set in W. But now we want to also show that they span W. So let W belonging to W be any element. Okay. Now what I want to do is that I want to consider this W along with these Wi's, but that will not necessarily give me M plus 1 elements, will it? Because this W may be one of these Wi's, be any element different from these, then the elements W, W1, W2, etc., Wm form a linearly dependent set in W. and I should perhaps already refill this. Okay, so we have chosen small w to be an element, a vector in capital W, different from this w bias. So these, along with these w i's, if I now take the extra w also, then I get m plus 1 elements which exceeds the maximum number m of linearly independent elements that one can have in W. So this new set is a linearly dependent set in W. So there exist scalars or field elements alpha, alpha 1, alpha 2, alpha m in F. F is the underlying field which is not there here anywhere, but you understand it's the underlying field in the background. Not all 0. We are now using the definition of linear dependence. Such that this linear combination is 0. Okay. If this particular scalar alpha is equal to 0, then this equation becomes what? Equal to 0 and linear independence of the W-wise would then imply that all the alpha i's are 0, because now this new linear combination involves only the W i's which are linearly independent according to our choice. So that is why all the alpha i's must be also equal to 0, just like alpha, but then all the scalars are 0, which is a contradiction because they cannot all be 0, not all 0, a contradiction. So we must have alpha non-zero, hence, but the moment you have non-zero alpha, you then have a way of expressing W itself as a linear combination of the W i's in this way. Minus alpha inverse alpha 1 W1 minus alpha inverse alpha 2 W2 etc. minus alpha inverse alpha m W n. Okay, and alpha inverse of course exists in the field because alpha is non-zero. Thus, these m linearly independent vectors they span W. Now behind this last conclusion here, there are some things. Note that we have chosen this small w to be an element in capital W different from these wi's. It may be the case that there actually is no such w, that capital W in fact is equal to this set. That can also happen. But if that is the case, then already they span capital W in a trivial manner, because the set formed by these w's is equal to capital W in that case. Okay, now there is one more thing. Fine, we have chosen W to be in capital W different from the wi's. Such a W is a linear combination of the wi's. So wi's span everything in capital W except themselves, but additionally they also span themselves in a trivial manner. That is because, for example, you can write W1 itself as a linear combination of the wi's, like this, in which only the coefficient of W1 is non-zero, which is precisely 1, and all the other coefficients are 0. And we are not explicitly writing that here. So at once we take all these things into account and conclude that thus these things span W. In other words, they already were chosen to be linearly independent. Now they have been shown to span W, so they form a basis of W. This shows that they form a basis of W. Hence, in fact, the moment we concluded that these finitely many vectors span W, we also have the conclusion that W is finite dimensional. But additionally, linear independence of these vectors allows us to now say that the dimension is precisely equal to n. Hence, dimensional and dimension of W is equal to m. And this m, oh, I forgot to write about this. We can write it here. This m must be less than or equal to n. Why? Because recall what is m? M is the maximum number of linearly independent vectors in W, which we have seen must be strictly less than n plus 1, because the moment we hit n plus 1 vectors, we have got a linearly dependent set in V and so a linearly dependent set in W also. So M cannot go beyond n plus 1. In fact, M cannot be allowed to reach n plus 1 also. So M has to be less than or equal to n, and that is how we have shown that W is finite dimensional and its dimension does not exceed the dimension of V. Next, we come to the question of the dimension of the quotient space V by W. Okay. From the basis so we now have this basis for W. Of W, we get the linearly independent set in V. Being a basis of W, this set is linearly independent. So we have already used the fact that we have not used the fact that this vectors span W. We have in fact shown that that is the case. Now again we are going to use the linear independence of these vectors in W, and so automatically in V also they are vectors, because W is a subspace of V and they are linearly independent in V. So we can blow this up to a basis of V by the previous corollary. By corollary 4, V has a basis of the form Wm and possibly some additional vectors Vr. Hence, because we are saying that this is the basis of V, so dimension of V is m plus r, the total number of vectors in this basis. And of course we already have this fact that the dimension of W is m. Now we will go to the quotient space. Here perhaps I should write what the author has written. I should precisely write that thing. Otherwise these things which appear in the text may remain confusing. So here what Herstein writes: let V1 bar, V2 bar, etc. Vr bar be the images in V bar, which is the quotient space of V by W of these vectors V1, V2, those extra possible vectors that we have needed in forming this basis of V from the basis of W. What does this mean? You see, when you see birds like these images and no function has been mentioned, you should understand that there is a natural something in the background, a natural function which is there in the background, which should be there. You are supposed to know that, and that natural function is just this. You know that there is an onto homomorphism from any vector space to this quotient space where W is a subspace of V. Just recall that same thing in group. You are given a normal subgroup of a group, then there exists a natural homomorphism of G onto G by N. Like that, there is a natural homomorphism of V onto V by W. In fact, from this we have this, because the vector space itself is a group under its own addition. And these images that we are seeing here are the images of these vectors under this map. And what is this map, by the way? Under this map, the image of the vector small v is the quotient V plus W. So all these V1 bar, V2 bar, VR bar, all these things you are seeing, they are just these. V1 plus W, V2 plus W, VR plus W. And that is why this sentence makes sense. Images in V bar, because these are elements in V bar. Okay, that's what they are. And in fact, for our own understanding, we will write what these things are. That is, now what we plan to show is that these V bars actually, we have already seen that they are elements in V by W. We now plan to show that they form a basis of V by W. For that, of course, we have to show these two things, that they span V by W and they are linearly independent over F. So let us show the span first. We now show that these span V bar. I think these short notations have been devised to minimize our writing. Okay. Span V. Let V plus W. We are, however, going to write the things, we are going to show everything for our own sake, for the sake of making things much more clear. So let this be any element in our quotient space V by W. We could have just written, the author, according to this short notation, would write that this same thing like this. And you can understand, okay, the meaning of these short symbols, but we still, we are going to write like this. So let this be any element in V by W. Our aim now is to show that this is a linear combination of these V bars. Then V belongs to V, and so we have, now you see, capital V already has a basis which looks like this. So this small v is a linear combination of these basis elements. So let's just write V as a linear combination of the basis elements plus, since we have other vectors, let's use some other, say beta 1, some other scalar names, beta r v r. For some scalars in F, then P plus W is equal to alpha 1 W1 plus alpha 2 W2 like that, alpha M Wm, beta 1 V1. I cannot possibly write the whole thing here. Okay, this is our V. I hope it is feasible. Alpha 1 W1 plus dot 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 plus alpha M Wm plus beta 1 V1, that is whatever we have here, we have written here in place of small v, beta r Vr plus W. Okay. Now using the operations we have in the quotient space, we can write this thing as alpha 1 times W1 plus W plus alpha M times Wm plus W plus beta 1 times V1 plus W, beta 2 times V2 plus W, that will come after this, which is there. Then beta r times Vr plus W. Okay. Now note that this is equal to W. The next one is also equal to W. Why? This you can see is V1 bar. This coset is equal to this coset because all these Wi's belong to capital W, so that's why the cosets are just W. Distinct cosets are disjoint. That fact is always there. Okay, so that's why all of these are equal to W. Oh, Wm I have written. This is just W. Now what is W? In the quotient space V by W, W is the zero vector, and you are multiplying the zero vector by scalars and taking their sum. So this entire part is going to vanish, and we will only have this. In this step, I am repeating again, we are using the fact that W is actually the zero element, zero vector in the quotient space V by W. That's why we don't have that. Now in the text it's this much of course has not been shown, only simply this has been written. Since as a justification of this vanishing, equal to 0. So you should understand that just like the V1 bars, W1 bar is W1 plus W, and all these things are 0 means what? This 0 is the 0 in V by W, that is this 0 is actually capital W, and that's why we have this. So what have we shown? We have managed to show that this arbitrary element of the quotient space is a linear combination of these V bars. Hence they span V bar or V by W, same thing. Next we show that these are linearly independent, and let's do that here. Next, let gamma 1 V1 bar, gamma 2 V2 bar, like that, gamma R VR bar equal to 0, and here again you should understand that because we are in the quotient space, this 0 is W, capital W. That is, and now we are going to write this thing in detail. Gamma 1 V1 plus gamma 2 V2 VR plus W equal to which is equal to zero, and 0 means W. So this coset is equal to W. That means this element that is giving us the coset should belong to W, which implies VR belongs to W, and because this is a vector in W, it will be a linear combination of that basis in W with from where we started all this thing. Thus VR is equal to a linear combination of the W-wise. For some scalars lambda 1, lambda 2 up to lambda m. Thus, so we can now take all things on one side and write this entire thing as minus lambda 1 w1 etc minus lambda m wm plus gamma 1 v1 etc plus gamma r vr equal to 0. This 0, however, is our 0 in the vector space capital V. It's not capital W. Okay. This calculation, the moment we have gotten rid of capital W, we have come to the level of the vector space capital V. We are no longer in the quotient space. Since these are linearly independent. Why? Because they form a basis of V. So all these scalars are going to be 0. The negative lambdas are going to be 0, which however we do not bother about them. Our concern are the gammas. So we needed to show that the gammas are all 0, and now we have shown that they are 0. Thus, these are linearly independent. We have thus shown that these vectors, these R vectors, form a basis of the quotient space. So the quotient space is finite dimensional, which however is not a part of the, it is there in the statement, but we haven't mentioned it explicitly in the statement, just like how we mentioned finite dimensionality of W, but it follows from here. So here also we are not going to write anything like that this is finite dimensional. We straight away write, so dimension of the quotient space is R. Now if you recall, this R is what? R plus M is dimension of V. So R is dimension of V minus M, and M itself is dimension of W. So that's how you get this formula, and here the proof ends. And there is one more result. Let's just see that also. It's also a formula involving dimensions of vector spaces, which looks like a formula from set theory about the number of elements in the union of two sets. It has that exact same structure. It's a corollary, and it is this. So this is the only corollary to this lemma, it was lemma, no? Yes. So there is no number. If A and B are finite dimensional subspaces of a vector space V, if A and B are finite dimensional subspaces of a vector space V, then A plus B is finite dimensional and its dimension is the sum of the dimensions of A and B minus the dimension of the intersection of A and B. Okay, so let's see the proof. Note that the original space V may not be finite dimensional, but the subspaces are finite dimensional. That is given. Since A and B are finite dimensional, A is the linear span of some finite set S and B is the linear span of some finite set T. Okay, for some finite sets A and B, S and T. Then A plus B is spanned by the finite set S union T. Why though? Any element in A plus B will look like what? A plus B, where this vector A is coming from A and B is coming from B. So A being from capital A is the linear combination of finitely many elements in S, and B is a linear combination of finitely many elements in T. So A plus B is a linear combination of finitely many elements in S union T. That's how S union T spans A plus B. And because S and T are finite, their union is finite, so that is why A plus B is finite dimensional. Hence, okay, Now we use one result of an exercise which we have already solved. By the result of exercise 13, of the first section on vector spaces, this quotient space A plus B by B is isomorphic to this quotient space A by A intersection B. This is something we have already proved in that exercise solution, but let's just note one thing. B is a subspace of A plus B in a trivial manner, so this quotient makes sense. Just like that, A intersection B is a subspace of A. We know that the intersection of two subspaces is a subspace, and it is contained in A, so it's a subspace of A. So this second quotient also makes sense, and these two quotient spaces are isomorphic. Now, finite dimensionality of A plus B implies, already it is there. I mean, A plus B is finite dimensional. That fact, in fact, is coming from finite dimensionality of A and B. So A and B are finite dimensional subspaces of A plus B, and A intersection B also is finite dimensional because it is a subspace of A. Actually, it's a subspace of B also, and that is why we are in a position to use the previous lemma. Hence, by the previous lemma, both these quotient spaces are finite dimensional. They are like V by W, and because they are isomorphic, they have the same dimension. And the previous lemma also calculates the dimension as the difference of the dimensions. So we have this dimension of A plus B minus dimension of B is equal to the dimension of this quotient, and that is equal to, due to this isomorphism, the dimension of this other quotient, which again by the previous lemma is the difference of these two dimensions. So you can now add dimension of B to both sides. So and that's what we wanted to show. So here the proof ends, and here this section also ends. After this we have the exercises, which we will start solving in the next vector space video. And here I end the video also, but before I sign off, tomorrow is Saturday, no? So tomorrow we have exercise problems from abstract algebra by Gregory T. Lee. One of you is waiting, right? So so that's just it. So see you tomorrow with Lee's abstract algebra. And on Sunday, of course, we have analysis. And oh, one more thing, that identity, this rule of exponent, that we were unable to successfully prove in the previous analysis video. Now I can handle that. I have found a way of proving this, and the great thing is that L sigma identity or that limit, which we have proved for only rational sigmas. There is no need to extend that to real sigmas. Whatever we now have, we can use only that and get this thing in a much simpler manner than what I was doing previously. Okay, so we will see this on Sunday. So see you tomorrow with Lee's algebra. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.